Hey guys, what's up? And welcome back to the Rocket Tub. My name is Philip, and today we are going to dive into the complex topic of reentry heating and how to overcome it. Thermal protection systems are extremely important for human spaceflight, and they are certainly something that you should know more about. We will be talking about heat shields in general here, but the ones of the Space Shuttle, the SpaceX Crew Dragon, and of course Starship are of particular interest. When thinking about the most important systems on a rocket, the first things coming in mind are probably the engines or maybe the avionics, but then you may be a bit weird. But whatever answer most people come up with, they all have something in common. They are needed to get this vehicle to either space or orbit. But especially in human spaceflight, rocket science isn't just about going up, but rather about coming back down. To bring your passengers back to the ground, you need to slow down from orbital velocity all the way down to zero. That means a change in velocity of about 7.8 kilometers per second, and getting rid of so much velocity certainly isn't easy. Using the engines to brake is far too inefficient, so engineers use aerodynamic drag to slow down. By re-entering the atmosphere at a very small angle, you can scrub off more velocity than by just falling straight down. But hitting the atmosphere at orbital velocity brings a lot of problems with it. Enormous forces created by the drag and an awful lot of heat. During the orbital re-entry, the windward side of the vehicle is tortured by immense temperatures. But why does it even get so hot up there? Let's take a look at the upper parts of our planet's atmosphere, about 70 kilometers above the ground. It is made up of molecules in a gaseous form, mainly nitrogen, oxygen, carbon dioxide, and a bit of ozone. There's a lot of room between those molecules, since the atmosphere is pretty thin up there. Now, let's take a vehicle entering the atmosphere into consideration. When it enters the layers of thin air, it displaces the molecules that were in the space the vehicle now fills out. The air molecules are pushed in front of the vehicle and get compressed in the process. The distance between the molecules becomes smaller. The pressure of the air in front of the vehicle rises and the temperature of the air increases. But compressing the air in front of the vehicle so much leads to that air being pushed out of the way, which creates a lot of friction, a process otherwise known as aerodynamic drag. In the process, kinetic energy from the entering vehicle is transformed into thermal energy and into the air around it. This conversion of energy actually sets free so much thermal energy that the air directly in front of the incoming vehicle becomes plasma. How much heat the vehicle actually experiences differs by quite a bit, depending on the velocity of the vehicle relative to the airflow. For example, a Falcon 9 doesn't need extensive heat shields, just a few heat-resistant materials covering the engines at the base of the booster. But then there's Starship or the Space Shuttle, with an entire side of the vehicle covered in thick and heavy tiles for thermal protection. But why do those two vehicles need so much more protection? Well, their re-entry speed is quite a bit higher. When the Falcon 9 booster returns to its landing site, it almost never exceeds Mach 7 or 8. The shuttle, on the other hand, entered the atmosphere with more than 25,000 kilometers an hour, more than 3 times the velocity of the Falcon 9, and Starship could even reach higher speeds when returning from interplanetary missions. The problem here is the formula which states how much heat is generated at different re-entry speeds. Unfortunately, the heating doesn't go up linear. If you think that it's going to rise by the square of velocity, then you're also wrong. Re-entry heating, designated as Q in this equation, goes up by the cube of vehicle velocity, meaning you generate 8 times more heat when going twice as fast. and Starship enters the atmosphere more than 3 times faster than the Falcon 9, so the heat difference is, well, let's say, enormous. In case of re-entering the atmosphere from low Earth orbit, the temperature of the air around the vehicle is able to exceed the 10,000 degree mark by a lot. Yikes! But heat shields don't experience the same amount of heat over the entire period of re-entry. The exact amount of heat the vehicle experiences mostly depends on velocity, atmospheric density, and resulting deceleration. During re-entry, the vehicle decelerates, it loses velocity and altitude, but at the same time the density of the air around the vehicle rises, leading to the heat that the vehicle experiences following a special curve that looks somewhat like this. One flat end and one steeper and with a peak in between, leading to huge differences in the actual amount of thermal energy that is set free over time. To get back from orbit without burning up in the upper atmosphere, you have to find a way to counteract the immense heat generated by your vehicle skimming through the air at hypersonic speeds. And that is where heat shields come into play. Heat shields are designed to withstand the immense heating during re-entry and protect the metal skin of the vehicle from this heat, since it exceeds the melting point of any metal alloy by far. Luckily, not all of the heat lands on the body of the vehicle. Most of the thermal energy actually stays in the air around the vehicle and doesn't get inducted into the vehicle's skin. Out of the multiple 10,000 degrees, just a small bit of the heat remains, but that is still enough to melt the vehicle entirely. To perform the work it is supposed to, the material a heat shield is made of has to fulfill a certain number of criteria. It has to be a pretty good thermal insulator, since the heat from the outside of the heat shield shouldn't get through to the skin of the vehicle or it will burn up in the atmosphere, meaning you would have the same result as going without any kind of heat shield at all. It also has to have a high melting point, so that the heat shield doesn't become a liquid during re-entry, which would be, let's say, problematic. Additionally, the material isn't allowed to be fragile, since re-entry and especially liftoff causes violent vibrations shaking the vehicle. The heat shield has to survive all those vibrations, so it is still intact until re-entry begins. And of course, the heat shield has to be as lightweight as possible, just as everything in rocketry, since it is all about eliminating as much weight as possible. Another aspect of designing a heat shield and entry profile is finding the perfect compromise between 4 criteria. Among them are the peak heat flux, the maximal amount of heat per area that the heat shield experiences during re-entry, and the heat load, the mechanical and thermal stress on the vehicle and its heat shield created by an atmospheric entry. Additionally, peak deceleration plays an important role, especially in manned missions, since the human body can't handle too much g-forces and decides the aerodynamic forces on the vehicle, thus having influence on the maximum aerodynamic forces the vehicle has to withstand. Speaking of it, the last factor is peak dynamic pressure, the maximum aerodynamic load the heat shield has to go through without breaking or getting damaged. To figure out these values, engineers simulate 2 worst-case flight paths, the overshoot and undershoot trajectories. The overshoot trajectory refers to a trajectory with the shallowest possible re-entry angle that is possible before bouncing off the atmosphere. The overshoot trajectory poses the highest heat loads on the vehicle, but a lower peak heat flux. The undershoot trajectory, on the other hand, is defined as the steepest possible re-entry angle. Due to reaching the lower atmosphere faster, the aerodynamic loads, the peak heat flux, and peak deceleration are way higher than usual. Every TPS material defines the respective overshoot and undershoot trajectories differently. When choosing a material, engineers try to get the corridor between these 2 worst-case trajectories as wide as possible. A heat shield's only purpose is keeping the vehicle's structure protected from the extreme temperatures during re-entry. In general, there are two different methods used to get the heat away from the vehicle. Either use the principle of convection or you go with radiation. The convection method creates a thin layer of hot gases that directs the heat away from the rocket and into the airstream around the vehicle. Most of the heat is blocked by this layer, letting only a small amount of it to actually make contact with the heat shield itself. The radiation method, on the other hand, takes use of materials with the ability to absorb great amounts of thermal energy. Heat shields taking advantage of this method first absorb the heat into the material and then radiate it away over time. As you can see, there's more than just one way of how a heat shield can work, and the two basic principles differ quite a lot in terms of material requirements. That automatically leads to two different design types of heat shields. Over the decades of space exploration technology development, many designs of heat shields have emerged. But due to effectively having just two basic principles to work with, there are also just two basic types of heat shield designs: ablative shields and thermal soak shields. Ablative heat shields are the type of heat shields that make use of the convection method. As the name states, they are able to disintegrate in a controlled manner. The heat slowly eats away the outer layers of material, which becomes gaseous due to the immense heat. These hot gases carry away the heat from the vehicle through convection, keeping the hull of the vehicle cool. Such ablative heat shields are typically made from a special plastic resin and only consist of a single piece, since they are wanted to not survive re-entry entirely. Since they disintegrate, they are also single-use items. Historically, ablative heat shields have been used on capsule-shaped spacecraft like the Mercury, Gemini, and Apollo spacecraft, and even on current vehicles like NASA's Orion and SpaceX's Dragon 2. But the far more interesting kind of heat shield is the thermal soak design. Other than the ablative heat shields, the thermal soak design is based on the radiation method. The material doesn't disintegrate upon contact with the plasma, but rather absorbs large amounts of heat and slowly radiates it away. During this process, the heat shield reaches temperatures of 1600 degrees Celsius and even above. Since these heat shields aren't dissolved upon re-entry, they can be used multiple times without being required to be replaced. Thermal soak shields are typically made from silica ceramics and reinforced carbon-carbon structures, depending on the exact amount of heat the specific part of the vehicle experiences. Since this kind of material expands slightly during re-entry and is fragile and brittle, it is usually manufactured in small tiles which cover the metal of the vehicle's hull. Thermal soak shields are primarily used on reusable spacecraft like the Space Shuttle, the Buran, and many others like Starship. Sometimes a thermal soak system is combined with an ablative shield. Since the sublimation of the resin used on these shields doesn't work below a certain temperature, some spacecraft use a second layer of protection beneath the ablative shield to ensure the thermal protection after the ablative heat shield stops working. In recent years, there were multiple attempts made to develop an inflatable heat shield, but despite having proven their capabilities, inflatable aeroshells never exceeded the experimental stages. Aeroshell designs aren't real heat shields. They reduce the peak heating by decelerating faster and higher in the atmosphere, leading such vehicles to have slowed down significantly when they reach the thicker layers of Earth's atmosphere, reducing the heat loads created. Apart from alternative designs like inflatable aeroshields, there are just two effective designs for heat shields. But there even are some ideas for thermal protection systems to be used during re-entry that require no heat shield at all. Heat shields are the most common re-entry heating countermeasure and have been used on almost every re-entry vehicle so far. But there are a variety of other countermeasures that engineers can implement, dropping the requirement for a proper heat shield. One of these other ways to re-enter the atmosphere is the well-known propulsive re-entry. On this kind of re-entry, the vehicle's engines are used to slow the vehicle down instead of friction. Not only does this method reduce the experienced heat dramatically, but is also far less violent than aerodynamic braking. But of course, there's a big disadvantage here, and that is propellant consumption. To reduce your speed from orbit velocity to zero, you need a lot of propellant, which has to be carried to orbit first. So basically, you either need a giant rocket or multiple launches to achieve a propulsive re-entry. SpaceX's Falcon booster uses a hybrid between the propulsive approach and the classical aerodynamic braking approach. It slows down with its engines, but shuts them down during large portions of the re-entry process to save propellant. That leads to some heat being generated in the process, but the Falcon booster blocks most of the plasma with cooler engine exhaust and additionally possesses some heat shielding. Another non-heat shield method of re-entering the atmosphere is, well, just ignore the heating and go in. The so-called passive cooling approach utilizes vehicle designs featuring metal superalloys and carbon compounds which are able to resist temperatures of 3000 degrees Celsius and more. After re-entry, the heat is slowly radiated away, giving the passive cooled re-entry its secondary designation, radiative cooling. Although this method is frequently used by supersonic and hypersonic drones and aircraft like the Concorde or the SR-71, radiative cooling was featured on a spacecraft only once. And that was on the earliest of all Mercury capsules, which weren't even going to orbit. Probably it isn't used anymore due to the immense cost of such materials. And the last, at least somewhat reasonable alternative is active cooling. Active cooling expands the double wall design normally used for the cooling of engine nozzles to the entire windward side of the vehicle. The cryogenic fuel flowing through the vehicle's hull functions as a heat exchanging fluid, absorbing most of the heat and effectively cooling the surface down. The warmed-up fuel is then either directed back into the tanks or bleeded off the surface through small holes. This bleeding approach was considered by engineers to be used on Starship originally, but that idea got dropped later in favor of a traditional thermal soak heat shield. There may be more ideas for non-heat shield designs, but these three are the most important ones. As you can tell from my examples, they aren't used very often for various reasons. Alternative designs are nice to know, but you don't really need to remember every detail when talking about re-entry heating protection. Heat shields play an essential role in getting back from orbit. Our technology is still dependent on the black layer of protective material when entering the atmosphere. Almost every re-entry vehicle of the past had a heat shield, and the next generation of spacecraft features them as well, no matter what kind. Heat-resistant materials enable humanity to leave our planet and have a way back in the first place. Through aerodynamic braking and heat protection, we have found a way to deorbit as efficiently as possible. Heat shields are essential parts of any spacecraft design and deserve far more attention than they get. Although they might seem simple, heat shields are a true wonder of applied physics. This video should be able to give you a decent bit of basic knowledge about the world of heat shields. I hope you could in fact learn a lot from it, and if you did so, why don't you leave a like and hit the subscribe button. Thank you if you do so. We see ourselves in the next video, and until then, I'm out. Cheers!